Hi everyone, this is chapter 9, Basic Quantum Theory. In this chapter, we're going to see a few concepts that completely revolutionize our understanding of nature. The first concept we're going to see is the concept of a black body radiation. In order to understand black body radiation, we need to go back to our electricity and magnetism course. In that course, at the end of the semester, we've seen that charged particles that are being accelerated will emit light. In any object, there is many trillion of atoms always moving and vibrating in all directions. Therefore, they will emit light at all time. And this vibration in motion, we can feel it as the temperature or heat of an object. So in other words, if we heat up an object, it will emit more light. And this is exactly the concept that black body radiation try to predict. First, what is a black body? So a black body is an object that absorbs all light that is being shone upon itself. So why should we study black body? Well, if it's absorbed all the light that is being shone upon itself, it's possible to create a model that predicts the intensity of the light versus the temperature. Now, in reality, there's not that many objects that can be approximated using the black body radiation. However, a few interesting objects like our sun or many stars can be approximated using this concept. Now, first thing is when we measure the different wavelength of light versus the temperature of an object, we will see a curve similar to this one. So in this graph over here, what we have is the wavelength in nanometer, the intensity in watt per unit area, and I've drawn on this graph three different curves. One at 4,500 Kelvin, it's the blue line. One in green at 4,000 Kelvin. And one in red at 3,000 Kelvin. Now, the goal here is to link the wavelength to the intensity or the power per unit area. The first law that was invented that was able to make the link between these two was Wien's law. And Wien's law states that the maximum wavelength multiplied by the temperature is equal to 2.898 multiplied by 10 to the power minus 3 meter multiplied by Kelvin. So what is the maximum wavelength? It is actually the wavelength that emits the most energy. So in our graph, it will be the exact peak of our curve. So these three peaks in this case. All right? The second law is Stephan's law, which links the intensity or the power per unit area to a constant multiplied by the temperature to the power 4. The constant over here is called the Stefan-Boltzmann constant, and it's equal to 5.67 multiplied by 10 to the power minus 8 watt divided by meter square multiplied by the temperature to the power 4. Basically what Stefan noticed when he was studying black body is that the area under the curve of each different black body at different temperature was roughly the same. And basically he made this relationship over here. And keep in mind the intensity is the power divided by the area. It's the complete intensity. It's not just the intensity at a certain wavelength. It's all the intensity emitted by this particular black body. Now, one thing we need to pay attention when we're looking at these type of graph is this point over here. And if we look at Wien's law over here, the maximum intensity, the maximum wavelength multiplied by the temperature is equal to constant, which means that if we were to increase the temperature, we would expect the maximum wavelength to keep increasing, actually decreasing in this case. But in reality, it does not happen. When we reach the ultraviolet radiation, there's a point where the intensity drops down. Okay, in all the exercise we're going to be solving in this course, this law will always be true. But in the next video, we will see how Max Planck was able to introduce a new concept in order to take into account what happened when the wavelength keep on decreasing. All right, so in the next video, we are going to be talking about Max Planck discovery, and it's a discovery that set into motion all the quantum theory. So see you in the next video.